Hello, everyone. The poster that we're presenting is about probing the two-neutrino exchange force using atomic parity violation. Now, it's been a well-known fact that the exchange of two neutrinos between two fermions produces a long-range force. The idea that we tried to pursue was whether this force could be probed in some other way than has been already known. For example, if we could probe this force in an atomic system. Now, neutrinos interact only weakly, which means that the force between two fermions because of neutrinos could, in principle, be parity violating. So our work was to calculate the parity violating force because of the exchange of two neutrinos between two fermions, and to see if there was any physical way we could probe this force in experiment. So we calculated this force, and we tried to apply the force to the system that is most common in nature, which is the hydrogen atom. So the force between the parity violating part of the force between the proton and the electron was calculated, and we tried to see if there was a way we can measure this. Turns out that there is actually a way we can measure this, and that is by measuring optical rotation of light in a sample of hydrogen atoms. What happens is, because of the parity violating nature of the force, left-handed polarized light and right-handed polarized light behave differently in a gas of hydrogen atoms. And so the optical transition properties lead to different refractive indices for left-handed polarized light and right-handed polarized light, which leads to optical rotation. So the idea is that if we can measure optical rotation in a sample of hydrogen atoms for high enough angular momentum states, then we can probably probe the neutrino force. The reason we need to do it for high enough angular momentum states is because for low states, the predominant parity violating force is the exchange of because of the exchange of the Z boson between the electron and the proton. So that would dominate entirely the neutrino force. But at high enough L, the Z exchange becomes lower because it's much short range because of the massive Z. And so we'll be able to see the neutrino force much more clearly. Thanks.